Hello, F-sharp. Welcome back. Today we're going to have a quick chat about memory management, stacks, stack frames, and heaps, what all those things are and how they relate to each other. And this actually came from a question that someone left on one of my videos where they said, like, hey, Matthew, could you spend some time talking about heap and stack and memory architecture so I understand what that means? Because in some of my videos, I reference those things quite a bit, but I haven't provided a video where I go into detail about what those things are, what they represent, and how they work. Now, I am not the expert on these things. So I will, at the end of this, I'm going to provide you some additional resources for you to go and check out, but I wanted to provide a nice little summary as a place for me to point people to, saying like, hey, here's a really quick synopsis of these ideas and how they work so that when you watch a video where I'm discussing them, you have some sort of context for what they're meant to represent. And I'm going to talk about computer memory architecture first. Then I'm going to talk about .NET memory management, and then I will talk about how they relate to one another. Now, something I believe I have talked about a little bit before, but we're going to go into is, how does the CPU work with memory? Well, memory in a CPU is in layers you can think of. And so at the very heart of the CPU, you have kind of two different elements. You have the ALU and the FPU. And there's actually more to that, but again, this is a simplification. The ALU is the arithmetic logic unit. And this is the actual piece of silicon that is doing addition of integers, subtraction of integers, comparison of integers. So all the different operations that you would want to do with integers. And it also works on bytes, N16, N32, signed, unsigned. So there's all these different low-level machine codes for doing these comparisons, and anything to do, well, essentially everything to do with integers of any kind is happening inside of the ALU, or the arithmetic logic unit. This is the thing that is actually doing the work. You also have FPUs, or floating point unit. It used to be that this was a coprocessor back in the day that you would have to add another processor in your computer to be able to do floating point operations. This is now built into it. And these two units for doing logic have registers. And a register is a place to store information, and it is essentially right next to these ALUs or FPUs. And there are different types of registers. They are of different sizes. So I'm not sure how much detail I want to go into this, but if you see things like RCX, this is a register address, for example. You also have the SIMD registers, which is what the FPU is typically working with. And so SIMD is an abbreviation, it's an acronym, sorry, for single instruction, multiple data. And so these will be registers that allow you to load a bunch of values into them. So you can think of it as just kind of an array of values inside of the very absolute heart of the CPU that the FPU is typically working against. I know I'm glossing over a lot of details for those of you who are hardcore x86, ARM people. And I will point you to the resources that go into more detail at the end. That's not the purpose of this video. But the important thing to know is that a register, whether it be just a normal register or a SIMD register, this is the information that is right next to the silicon that actually does logic inside of your CPU. Now, there are very few of these. And part of the reason is just because of space. Like a CPU is kind of laid out on this grid of transistors. And all CPUs are actually 3D at the end of the day because they have wires going up and down that are connecting the different transistors inside of it. So but you kind of have this, you're dealing with the reality that a CPU is a very planar device. And so there's only so much space. Like if you have, for example, if this is your ALU here, you only have so much, square nanometers around it that is actually physically available for you to put a register. There's only so much room, and registers do take up space. And so there's only so much space around it. So that's why there are very few registers. Now, how many registers are actually in a CPU? We don't know. There are the addressable registers that you will see if you're reading x86, like, hey, these are the register codes or register addresses that you're allowed to use on x86, but don't for a moment think that that is actually physically how many registers are actually in there. There's way more, but we're not going to go into that. Okay, we've gotten through the first layer. Then, okay, after registers, you have the L1 cache. And the L1 cache is a little farther away from the ALU and the FPU, the very nerve center of the CPU. And it is typically very small. It is very fast. It typically takes 2, 3, maybe 4 CPU cycles to get a value from the L1 cache into a register for you to work on. And each CPU core has its own L1 cache. L1 caches, there may be some weird CPU where the L1 cache is shared between CPUs, but that would be a very bizarre design choice. But you can essentially think of the L1 cache as being a dedicated set of memory right next to the ALU and the FPU and the registers. It's very quick to access, but this is typically very small. We're only taking a few K of space at most. So it's very, very small. So it's very limited. And again, you're dealing with this kind of geometry problem. There's only so much physical space next to the ALUs and FPUs. And yeah, you only have so much room to put silicon. And so what happens is when your program is running, the value it needs is not in the register. It'll first check, hey, is it in the L1 cache? And if it is in the L1 cache, it'll load it to the register and life is good. But because of the limitations of the L1 cache, its size limitations, we also have an L2 cache, which is much larger, but is slower to read from. So we're talking about tens of cycles at this point to be able to read something from L2 cache. But it's much larger, so you can put much more into it. Now, again, with modern CPUs, L2 caches are very rarely shared. I don't know all CPUs, so I can't say like, yeah, there are no CPUs which have a shared L2 cache, but I think it's very unlikely because, again, they are very small. You then have what is most CPUs, I believe, now have the L3 cache. And the L3 cache is typically shared between the cores on that die. And so you can have multiple sets of ALUs and FPUs that are all sharing the same L3 cache. This is typically on the same die. With the new processors coming from AMD and now from Intel, you will have, if you look at them physically, you now have things where you have multiple pieces of silicon on the same packaging. And one of these will be like the IO die. And then this will be a compute die. And this will be another compute die. And inside of these, there could be like different cores. So you have core 1, core 2, core 3, core 4. And each one of these has their own L1 and L2 cache, but then they all share some L3 cache. But this L3 cache is shared between the cores on this die. It won't be shared with the cores on this die. And again, this is an ever-evolving thing. I think now with Zen 4, you might actually be able to share the L3 across these 2 compute dies. But again, it's getting very exotic. The important thing to know is that L3 cache is still very fast. It is still most likely on the same silicon as the core. And just through the speed of light, it's going to be relatively easy for you to get, and it is much larger than the L2 cache. But what if our program is still taking up more space? Well, then now, once you go beyond the L3 cache, now you're talking about main memory. And by main memory, we are typically talking about RAM. And so this will be like your DDR4, DDR5, whatever that may be. Now, reads from main memory are very long. So we're talking, greater than 100 cycles to get something from main memory. And so we try to write algorithms that fit inside of the cache of the CPU, and we try to write algorithms that fit inside of the cache. That's not always possible. Sometimes it will spit out to main memory. Now, CPUs are marvels of engineering, and they will see your access pattern and say like, hey, you're reading through this array in linear order. I can see what data you're going to need. And so it will preemptively load data from main memory into the cache, because it's like, hey, it's very probable that you're going to actually need this memory. So the CPU is doing everything it can to try to speculate about what memory you're actually going to need and load it for you. And so the performance hit of having to read from main memory can be hidden by the fact that the CPU is so smart, it knows what data you're going to need, and so it's reading it in for you ahead of time. And if for some reason things get really terrible and your data doesn't even fit into main memory, you can start paging to disk. So you have some kind of hard drive way out here. Now SSDs have gotten a lot faster, but again, if you're getting all the way out to here, you're having a really bad day. So takeaways is that the CPU is composed of this nerve center of an ALU and FPU, and I realize there's more there, but for the sake of simplicity, the ALU and the FPU are only able to work with the registers, which is the memory that is right next to them. If it doesn't fit in the register, it's got to go to L1 cache. If it doesn't fit in L1, it has to go to L2. If it doesn't fit into L2, it goes to L3. If it doesn't fit in L3, it goes to main memory. And the point is, there's a significant performance hit between each of these levels of memory. If you're constantly having to go out to main memory, your algorithm is going to be slow, but the CPU is doing everything it can to help you. Okay, that's a really quick intro to kind of memory architecture for a CPU. Let's talk about a .NET process. So when we talk about and we'll just talk about fsharp, right? But this is also true for fsharp, C#, and VB.NET. We are often talking about like, oh, well, there's the stack. And we have things that are allocated on the stack, and and we might even draw it like this. Like, hey, we have the stack and we have these values in the stack, and then we have the heap, and it's some abstract piece of memory over here, and we often kind of draw it as this cloud-like object. Like, oh, well, I have this array and it's allocated in the heap, and I got another array, and I might even have a dictionary or some other thing out here. And these collection types are allocated on the heap, but then we have stuff allocated on the stack, and we know the stack is fast. When we allocate to the stack is fast. And we have values in here where it's like, oh, well, this could be an integer, and this could be a float. And as our program runs, we are putting things on the stack. We are growing the stack down typically. And then as we run, we'll be allocating kind of up and down the stack as we add stack frames. And this is typically kind of the level of abstraction that we think about when we think about fsharp, C#, and VB, not VD.NET, VB.NET. And we say okay, well, great, but how does that relate to the way a CPU is thinking? What's the connection? Because I don't know about you, but when I look at the CPU diagram, I don't see a heap here. I don't see a stack here. I don't see any stack frames. What is that? That is a good question. how does this interact with this? Because we know that our fsharp, our .NET code has to run somewhere, but what is that mapping? That is a really good question. So let's talk about what these things actually are, the stack and the heap. Now, when your process kind of starts up, we have, let's say we have this giant array of memory here. So we're going to call this this is just the memory of our system. And it goes from high to low. And so this low address here, this would be an address of 0, 0. This is null right here. And this is that there's a page of memory there. And up here, we have this idea of what is called the kernel space. So this is a portion of memory that is only available to the kernel. So whatever operating system you are running on. And then at the very low end, we want null addresses to be invalid. So this isn't allowed either. Okay. This does map to the memory available on your system, right? It is the addressable memory space that your computer can actually address. But when your program starts up, it has this space available to work in. And this space is called user space. And this is the addressable memory space that your program can use. And I'm glossing over a lot of details. I'm not talking about virtual memory or anything like that. But this overall memory does map to that physical memory. And when we create a process in .NET, a certain portion of this will be allocated to the stack. So like, hey, these physical memory addresses, because each of these has a memory address that corresponds to it. This section, this 4 megabytes of our machine is set aside for the stack of this program. And this space over here, this set of memory addresses, we're going to use that for our heap. But .NET completely hides this from you. We then have some additional space for, I'm going to call program values. And I'm not going to go into the details of what's in here, but this little section here is kind of set aside for some of the constants of our program. But the stack and the heap are a set of real memory addresses in our computer. And so when we talk about like, oh, this abstract idea of the heap, well, this abstract idea of the heap, it's this set of memory addresses here. This is your heap. It is actually an addressable space, and the .NET runtime is managing that space for you. And the stack, again, is a set of memory addresses that is in user space that the .NET runtime is managing for you. And what is happening is the CPU sees these addresses and sees how your program is running and will load these addresses in as it needs them. Now, the question I kind of want to answer now is why do we talk about like, yay, we should allocate things on the stack and have stack allocation, and the stack is fast and the heap is slow? And whenever we allocate something on the heap, that is slow. Well, those are not correct statements. Well, they are incomplete statements. Allocating on the heap is not slow. It is actually very fast. And when you want to create a new object, it is incredibly quick. The .NET Runtime is highly optimized for creating new instances of objects on the heap. And the way it's doing that is well, there are different strategies, but it's very easy for it to create new objects in this area. The problem, though, is that this is divided up into sections that may or may not fit into cache. And so as your program is running, your heap, may be over here. Because not all of your heap can fit into the L1, L2, or L3 cache. And so your stuff that's on the heap may be all the way out in main memory. And so the .NET Runtime is having to bring things into cache and then push things back out to main memory because the entire heap doesn't fit in. The stack, on the other hand, the stack also can exist in main memory, but the thing is, the stack is typically a much smaller piece of memory, typically 4 megabytes, and this is something that you can adjust, but typically it's 4 megabytes of space, and it is almost always hot. And what I mean by that is that when your program is running and you're putting things on the stack or removing things from the stack, your CPU is always working on that set of memory addresses. And the CPU sees that and says, oh, you are almost always working with these memory addresses. I need to keep them all in cache. And so it is very unlikely that a piece of data that has been allocated on the stack ever gets moved all the way out to main memory, because the CPU says like, oh, this data is always hot. It's also very small. It's only 4 megabytes. And so it is very easy for your stack, I'm going to put stack, to exist in this space and just be entirely contained within the cache. You almost never need to store elements of the stack out in main memory. I mean, if you pause your process and then the CPU is swapping out a different program, it will move the values of your stack out to main memory, but then it will bring them back in as it needs to start working on it. So and if we're being really correct, the stack actually kind of exists between all these different areas. So the stack almost always is fitting here in the caches of your CPU. And again, the heap also exists across all these memory hierarchies, but there's a greater probability that pieces of the heap will spill out to main memory, and then your CPU will have to bring them in and out. And so we like to keep things on the stack when we're trying to write high performance code, because it's almost guaranteed that that data is going to be in the caches of the CPU. And so we're not going to have these cache hits and have to go all the way out to main memory for value. Now, if your heap is very small, it is possible for your heap to also fit in main memory. And a lot of what I do is I'm trying to write code that keeps things very small, especially with modern CPUs having giant L3 caches. This is even more feasible. But if your entire program, both the stack and the heap, can fit in the CPU's caches, it is going to be an incredibly fast program because it's never going to have to go all the way out to main memory. And this is why I even have this channel, is to help people understand like how to write programs so that they actually are smaller and fit in these spaces. Because once you have to go out to main memory all the time, your performance is not going to be as good just due to physics at this point. So I hope that was helpful. It was meant to be a kind of a quick overview of like what I'm referring to when I'm talking about these different aspects of the CPU and of .NET programs when they run, the stack and the heap. Like the stack and the heap they physically exist in memory, but they could be being moved in and out of caches and then out to main memory. If we are able to write small programs, they're able to run faster. So there are some fantastic resources to learn more about how all of this works. The first one I would recommend is this book, Pro.NET Memory Management. It is a fantastic book by Conrad Kokosa, and it goes into incredible detail about how the .NET Runtime manages its memory. They also have a website where they offer training, and they have some fantastic workshops. If that's the way you like to learn, they also have a wonderful YouTube channel where you can get a lot of this content for free. So they are a fantastic resource to reach for to learn more about this. Another book that I recommend if you want to get deeper into how CPUs actually work is this one. It is a fantastic resource, Modern Computer Architecture and Organization. I've really enjoyed reading this one. I found it very helpful and easy to follow. And so if you want to get down into the depths of how CPUs work and so how you can write fast code, those are the things that I would recommend. So I hope that was helpful. I really appreciate you taking some time with me. If there are aspects of the .NET Runtime and performance or CPU architecture that you would like me to go into deeper detail, please let me know down in the comments. I really enjoy this stuff, but I want to make sure I'm creating content that is helpful for you. Until next time, have a wonderful day. Thank you. Bye-bye.